الرحیم. امروز روز دوشنبه هست، 22 فروردین ماه 1401. جلسه دوم حضوری درس زمین آمار هست. در خدمت عزیزان هستیم. اشاره‌ای داشتیم درس قبل به مطالبی که در 12 جلسه مجازی خدمتشون گفته بودیم به منظور ایجاد انسجام، اینتگریتی بین مطالب جلسات قبل و مطالبی که بیشتر کار ریاضی داره و بنا داریم که تو جلسات حضوری بهش بپردازیم. If I want to connect our today's discussion to what we said in our previous lecture, once again I have to state the problem again and then try to arrange for a framework to see how we can solve this problem. Given a single partial realization of a random function then we are asked to estimate the attributes under consideration at a point which is not sample. Please pay attention that in various textbooks written on geostatistics, this Y uppercase letter is denoted by Z. And this argument here is denoted by U. And when you are reading a typical textbook written on geostatistics, you have to connect. You have to interchangeably use Z instead of Y, U instead of Z. Even I would suggest to replace the notation in our own notation and try to reproduce what is given in a typical textbook. And this is very unfortunate, I would say, that one obstacle toward effective and efficient learning is that different textbooks written on the same subject use different notation. And this is very unfortunate. I do have a justification for Y instead of Z, because the lowercase letter and uppercase letter seems the same on the board, if not on the written in textbook. That is why I will use Y for representing a typical random function or random variable. And then, since the space starts with S, I will use S instead of U. These are our data, and then we would like to estimate Y at the point which is not sampled. In first province, we have 163 non-recording ranges, which means our province is the fourth province around the country in terms of area, which means that it is not possible to monitor precipitation at every point in a space, but only 163 ranges. That is what we mean by partial, because we cannot monitor the entire study area using recording and non-recording ranges. And by single, we mean we have only one number at every point, even though we represent the attribute under consideration by uppercase letter. if I want to be correct, I have to represent this by lowercase letter because we have only one number. But because our framework is stochastic, we deliberately represent y by uppercase letter to tell you that we are working within a stochastic framework. These are our data. And then we have to go through 3 steps to solve this problem. The very first step is to understand our data. By understanding our data, we mean we have to clear our data, we have to delineate direction of maximum continuity and minimum continuity, which means we have to decide whether we want to consider our random function to be isotropic or anisotropic. We have to decide whether our mean is constant or variable. We have to decide whether our variance is constant or variable, and you know for sure that as soon as you make a decision on your data, you have a clear picture to go ahead and solve this problem. And this is again another part of the unfortunate part of the story is that if you are given a series of data like this problem, you cannot say beforehand which estimator will give you the best goodness of fit criteria. You cannot say that. You have to go through the process, you have to solve the problem, find the goodness of fit criteria, and then tell your audience which estimator is going to be the best. Step 1, exploratory spatial data analysis. The acronym for exploratory spatial data analysis is simply the first letter of these 4 words. Exploratory spatial data analysis. If you have a chance to work with ArcGIS as a typical module in this software, then you can find a huge document on exploratory spatial data analysis, ArcGIS. When I was working on this software at 90, the name was not ArcGIS, the name was ArcInfo. And I have to use a module so-called grid to delineate depressional areas versus non-depressional areas using grid module of ArcInfo. That is the first step. And for the last 10 years or so, our major contribution in geostatistics concerned with this exploratory spatial data analysis. I will try to share a number of papers written on exploratory spatial data analysis with you to see what do I mean by saying our contribution concerned with exploratory spatial data analysis. And we do have a large number of unanswered questions in this case, for which even myself have no answer at the moment for exploratory spatial data analysis. The second step which is very applicable from now up to the end of the course, these 3 steps. Variography, or structural modeling, or variogram modeling. 3 names. Variography, or structural modeling, or variogram model. Are you changing the camera as I move from here to here and so on, or just it is fixed? No. Are you changing it?
Okay,
it's okay. Step 3, as soon as you have the model of spatial variability at your disposal, you are ready to go for estimation. Step 3. When you see a topic like step 2, the very first question that might hit your attention is this. Mr. Abedin, in your previous lectures, you argue that we have to measure, to quantify a random function. Measure of similarity, measure of variability. And when it comes to measure of similarity, we have 2 index, covariance function, correlation function. When you are talking about measure of variability, that is the index corresponding to measure of variability. The question is, why do we talk about variogram and not covariance function? Why do we write step 2 as variogram modeling and not covariance modeling? This is a very important question, and you have to have a clear answer for this question. Why do we prefer variogram as measure of variability over covariance or correlation function as measure of similarity? We consider 2 important reasons to prefer variogram compared to covariance or correlation function. What are those 2 reasons? If you look at the definition of covariance, by the way, in my previous lecture on Saturday, I wrote the definition of covariance function between 2 random variables. If I want to switch from statistics to geostatistics, again I do have the same definition for covariance with minor change in notation. Look at the minor change in notation. That is the covariance. And then I have to write a random variable here. Instead of writing x, I will write x, y as a function of si. And you know for sure that y at si implies that you have a random variable. Because even though I did not write omega, but omega is in place. Therefore, this is a random variable. And then y at sj is another random variable. We have 2 random variables in a space. And this arrow on top of S implies that it could be 1D, 2D, or 3D. When you are in geostatistics, you could replace this by R as a function of SI, SJ. Which means by now your covariance is a function of absolute location. If you want to quantify your covariance at this stage, you have to specify 6 arguments for R to be quantified. What are those 6 arguments? If you are, of course, in 3D. 3 arguments for SI and 3 arguments for SJ. That is what I mean by R being a function of absolute location. And then how we are going to define it? Expected value of Y at SI minus M at SI Y at Sj minus M at Sj. Please look at how I consider writing. I have to start with this, and then this, and then this. And that is the correct writing, the correct way of writing when it comes to various sign for honoring first parenthesis and then bracket and then number. As you can see, and this is the unfortunate way, that your covariance definition is M-dependent. It depends on M, mean function. And no doubt, if you switch to covariance correlation function, then correlation function between 2 random variables Si and Y at Sj can be written as rho as a function of Si, Sj. And then we define correlation function in statistics or geostatistics by R Si Sj divided by R Si which is the variance of Y at Si. See, Si imply that here you have Si, which means that it is R Si, and it is Si, which means that the expected value of this to the power of 2, and then expected value of this to the power of 2 is basically the variance of Y at Si. Times R Sj, and then you have to raise it to the power of 1 over 2 to make it dimensionless, because it is a variance, not a standard deviation. And you have to raise it to the power of 1 over 2 to to make it consistent with the numerator in terms of unit. This covariance function lies between -1 and +1. These are measures of similarity, which is very applicable to time series analysis. When it comes to variogram modeling, and I would like to write it here and then tell you the reason that I talk about in my virtual lectures, variance of the first increment is defined as variable, 2 times variable. Variance of the first increment is considered to be 2 gamma Si Sj. When I'm about to explain in some detail the exploratory spatial data analysis, I will try to derive this relationship for you, where this relation is coming from. موقعی که خواستم نقل اکسپلوریتور اسپیشال دیتا صحبت کنم، این رابطه رو بهتون ثابت میکنیم که این از کجا به دست آمد. چون ناتوی از استاتیستیکس میدونید، ولی ناتوی مربوط به استاتیستیکس نیست، این مربوط به جیو استاتیستیکه. خدمتتون. Now, why do we prefer variogram over covariance or correlation function? 2 reasons. First reason, definition of variogram is M-free. There is no need to know M. As you can see, there is no M in definition of variogram. But when it comes to covariance function or correlation function, it depends upon M. And then you may ask, what is wrong, what is the problem with knowing or not knowing M? The question, as I said in my previous lectures, if you want to prove stationarity cannot be proved. Stationarity is the property of your model, not the property of your data. You will impose stationarity on your data. Why? The very first condition for stationarity is that M has to be independent of spatial location. M has to be constant. How could it be possible to prove that M is constant when you have only a single number at every point in space? If you have a single number at every point in space, then it is not possible to talk about expected value of this value or expected value of this value. Therefore, stationarity is considered to be the property of your data. Again, when I'm talking about exploratory spatial data analysis, I will give some graphical representation to tell you what do I mean by constant, mean variable, mean constant variance, variable variance in more detail. The second reason for preferring variogram over covariance or correlation function. The second reason is more or less theoretical. Why is it theoretical? Today I'm going to solve a typical example where I will refer to this second reason as well. Look at this problem. If you realize that your random function is not stationary, and I invite you to look at a number of references like Kitandis or Guaretz to see if covariance is defined for variable mean. And you realize that in Kitandis, the derivation of Kriging for variable mean assume that the Kriging system is written in terms of residual, not in terms of the original random function, which means that if you decompose the random function into two components, deterministic component and stochastic component, then Kitons assume that your stochastic component is stationary. And then as soon as you assume that your stochastic component is stationary, then you can test your Kriging system in terms of covariance of stochastic there. But if your stochastic term is not stationary, then you can't talk about covariance function. Now, in Persian we have an idiom telling you her gerduی گرده ولی هر گردی گردو نیست. What do I mean by this idiom in our own discipline? If your random function is stationary, then it is intrinsic as well. But if your random function is intrinsic, then it is no longer stationary. Stationarity would give rise to intrinsic hypothesis. But intrinsic hypothesis cannot be given rise to stationarity. If you have a stationary random function, then you can cast your Kriging system in terms of either variogram or covariance function. But if your random function is not stationary, you can only cast your Kriging system in terms of variogram. If I want to put this second preference in another terminology, I would say, if you have a process where the random function corresponding to that process is not stationary, then you can still solve this problem, but not with covariance function or correlation function, but only with variogram function. That is the second reason for preferring variogram over covariance function. Now, let me stop at this point, because every lecture that we are going to cover something, we will repeat the entire course. That is the reason for not concerning ourselves about what we said before, because at every lecture we are going to cover the entire material that we are going to teach in this course. Therefore, let me start to solve this first problem that I raised in my previous email, tell you what the problem is and how we are going to solve it. The problem statement is this. Linear model in 1D. This question is designed to concern a random function having a linear variogram. Let WR be a set of independent random variable. Let Wi be a set of independent random variable. the values of +1 and -1 with equal. By the way, this question is a typical question given in exam, either midterm exam or final exam or comprehensive exam. Let Wi be a set of independent random variables that take the values of +1 and -1 with equal probability. We try to create a random function using this random variable. How? A regionalized variable better to say a random function y uppercase letter as the function of n is constructed, is built for positive integral values of n. By summing the Wi up to n. Y at n is equal to summation I from 0 to n Wi. If n is 0, then y at 0 will become W0. If n is equal to 1, then you have I from 0 to 1, which means that your y at 1 is equal to W0 plus W1. If n is 2, then you have W0 plus W1 plus W2. From here to here is what you are given. You can classify your given and find to be these are given, and then you are asked to answer the following two questions. The very first question: show that Yn is not second order stationary. Show that y of n is not second order stationary. And then you are asked in the second part of this question that show that y sub n is intrinsic with linear diagram. If you are given this problem and you want to see if you can solve this problem using what we said from the first session to now, then sooner or later you will realize that you need to know the basics. What are the basics? Basics are coming from statistics, not pure statistics. Let me try to interpret the question itself, put it in our mathematical framework, telling you have to specify your objective, you have to convert your objective into a conceptual model, and then you have to convert your conceptual model into mathematical model. And then as soon as you have mathematical model at your disposal, then you are ready to solve it. یه فریمورکی بهتون دادیم، یه جدیدش فلوچارت بهتون دادیم که تقریبا توی 4 تا کورس که تو کار من دکترا عرضه میکنم، این 4 تا کورس شامل این 4 تا درس میشه: هیدرولیک محاسباتی، هیدرولوژی محاسباتی که این باشه، ریاضیات عالی مهندسی 2 که مزاحم صفحه خانم رجب زاده شدیم، البته سعادت نداشتیم در خدمت شما و درس روش‌های عددی در مهندسی منابع بود. این 4 تا درسی هست که در مقطع دکترا میدیم، 9 تا درس هم در مقطع کارشناسی ارشد. توی 13 تا درس این فلوچارت مشترک. تو زندگی زناشوییتون هم این فلوچارت به درتون می‌خوره. میگی نه، give it a try. What does that mean? When I say it will be used in your social life as well. In your social life, you have to have an objective. You have to convert your objective into a conceptual model. And you have to see how you can overcome your life problem. According to the advice received from Einstein, you have to spend 50% of your time on understanding the question itself, and then allocate another 50% on how to solve it. Let me interpret the first sentence. Let Wi be a set of independent random variables that take the values of +1 and -1 with equal probability. This random variable, at first we have to decide whether it is discrete or continuous, because it will affect our decision on how to solve it. If our original random variable is a discrete random variable, then we have to follow one route. If our original random variable is continuous, then we have to follow another route. Can I give a real example of a typical random variable that behaves like this? Yes, why not? If you throw a coin, the result of doing this experiment is either tail or head. As soon as you throw a coin, you have to consider a sample space for the result that you are going to get. That result will make up your sample space. Therefore, if you throw a coin, the typical example or experiment of throwing a coin has either tail or head. If you represent the random variable for this statistical experiment by x, then this x will act on your sample space to give you a number. Therefore, by throwing a coin, you are going to have a sample space. And the sample space for this simple experiment is either h or tail. We will denote the sample space by omega, the inherent randomness. This x, this random variable x, will act on omega to give you a number. And if you refer to my previous lecture, under the stochastic umbrella, I talked about 4 possibilities. The very first possibility is to have x only a function of inherent randomness. The second possibility is to have x as a function of time and inherent randomness. The third possibility is to have x a function of S space and inherent randomness. And the fourth possibility is to have a spatial temporal phenomena. Therefore, if you throw a coin or if you throw a disk, you are talking about a purely random process where the random variable has only inherent randomness as the exclusive source of variability. And then you will argue that this is positive 1 if omega is equal to h. And it is equal to -1 if omega is equal to t. That is how we interpret throwing a coin or throwing a disk. All you need to do, if you want to see what is this W here, the W out there is simply this X here. And it says, let Wi be a set of, now, what is this independent? This independent concerned with repeating this experiment numerous times. And this will give you W0, W1, W2, W3, W4, W6, and so on. And by independent, it implies that the covariance between Wi and Wj is 0. Okay? What I'm trying to do is just trying to interpret the question. This is given and this is fine. This is the objective. Now the conceptual model is this elaboration, this interpretation, to understand the question itself. How could it be possible to interpret Wi for a particular I, of course, is this. All you need to do is to replace this X with W. And then, with equal probability, the probability of having probability of having W equal to H is 1/2. Probability of T is 1/2. Perhaps, how should I write it to include this plus 1 and minus 1? Here, this is the numerical value that this could take, and this is the index corresponding to inherent randomness. Therefore, that is one possibility to represent probability of receiving omega to be H is 1/2, and probability of omega being T is equal to 1/2. And now we will use this source of variability to create random function. If you want to write this voice of n in full term, one possibility is to write this as n and source of variability. W. That is another way of writing this random function, because this n here implies the time or the space, but the time or the space is integer, not with significant digit. This n here implies time or space, but not significant digit, but integer. But this WR here is the index corresponding to inherent randomness. And how we define our random function is one here. We have a 1D random function. This is the 1D direction. And then for various values of n, 0, 1, 2, 3, and so on, when you are here, if you want to tell your audience what is the value of y at 0, you have to replace this n with 0 and see what will happen. It will give you W 0. And this W0 could take the plus 1 or minus 1. This W0 is like x here. If you are here, let me write it here, it will become W0 plus W1. And I will talk about the numerical values that y at 1 could take. When you are here, you are going to have W0 plus W1 plus W2. I'm just trying to replace this and with various numerical integer and find voice of. And then here, y at 0 could take either plus 1 or minus 1. But if you are here, you have to see what are the combination for this W0 and W1. W0 could take either 0 or plus 1 or minus 1. W1 could take either plus 1 or minus 1. And then you have to combine this to see what would be the scenarios that would take place. This W0 could take, let me write it with different color. This W0 could take plus 1 and minus 1. Freeze W0 at plus 1 and then change this W1 with plus 1 and minus 1 to see what will happen. If W0 is 1, then with this one here it will give you 2. Therefore, the numerical value for this random variable at yn is 2. And then if w0 is 1, but w1 is minus 1, then it will give you 0. Now, assume that this w0 is minus 1. And then change this to what you have for w1. Minus 1 plus 1, 0, which cannot be written again because 0 and 0 is the same. Minus 1, minus 1. That will give you minus 2. These are three realizations for this random variable at yn. Y at n, y at 1 could take either 2 or 0 or minus 2. But y at 0 could take only plus 1 and minus 1. When you are here, you have to see what are the combination for these three values. Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. Combine them to see the number of permutations that you are going to take. Is there any other scenario or alternative for this? Can you delineate some other combination? Plus 1, this could take the plus 1 or minus 1. For plus 1 it will give you 2, and minus 1 it will give you 0. And then if you freeze this by minus 1, then this could be plus 1 and minus 1. That will give you minus 2 and 0. 0 cannot be repeated again. Therefore, you have three possibilities for random variable at yn. This is y at 0. This is y at 1. And this is y at 2. And you know for sure that at every point for various values of n, you are going to have a random variable. Their aggregation will give you a random function. I'm still talking about conceptual value. Now, I have to interpret these two as well. Part of the conceptual model. Or better to say, moving gradually from conceptual model to mathematical model. If I want to show that my random function is not stationary, I have to know the properties of a stationary random function to be able to show that y sub n is not stationary. I have three conditions for a random function to be stationary. What are those conditions? Condition number 1. For a function to be stationary. The very first condition for stationarity is to have the expected value of y at generic n to be constant, independent of n. That is the first condition for stationarity. Expected value of y at the typical n, generic n, not particular n, has to be independent of n, index of space or time. The second condition for stationarity is to have variance of y at a generic n to be independent of n. The third condition for stationarity is to have covariance of I and Y at Nj, these are two random variables. The covariance between these two random variables, which can be written in shorthand by R to be a function of Ni, Nj, and there is no need to put arrow on top of this, and you know for sure why, because it is 1D, there is no need to put arrow on top of it. And for your random function to be stationary, this R should be a function of separation length. These are three conditions for a random function to be stationary. If you want to show that a given random function is not stationary, at first you have to check the first condition. If it happens that it will satisfy the first condition, then move to the second condition. If it happens that your random function satisfies the second condition, then you have to move to the third condition. If it happens that the random function satisfies the third condition, then you will say that your random function is second order stationary. Second order stationarity has something to do with this variance and covariance. Okay? If it happens that only one of them is not satisfied, then your random function is not stationary. Here, you will notice that the first condition is applicable, but the second condition is not applicable. The second condition cannot be satisfied. Therefore, your random function is not stationary. How could it be possible to show that expected value of y is depending on n or not depending on n? You have to refer to basics. You have to refer to definition of your random function. You have to replace this, let me write it again. I have to replace y with its counterpart. And since this operator is linear, I can bring it inside. Because expectation operator is a linear operator, I can bring it inside and then put the summation outside. Now, I have to compute the expected value of W at the typical I. The question itself says your Wi is a discrete random variable. And if your random variable is discrete, you have to refer to a particular equation to find the expected value. If your random variable is continuous, then you have to use another relation. I gave that relation in my previous lecture. The expected value of x as a typical random variable if x is discrete, is given by summation j from 1 to n p sub j times x sub j. This is how we define expected value of a discrete random variable. How can I interpret this p sub j and x sub j? As you can see, this x is discrete. Therefore, the sample space corresponding to this x is a numeral. شمارش پذیره. And here, for this particular case, is 2. Because we have two possibilities, plus 1, minus 1. This x of j is the numerical value that x could take. Look at this x here. The plus 1 or minus 1. And then this piece of j is the probability associated with x of j. If the probability for the first possibility is 1 over 2, the probability for the second possibility is 1 over 2, then that means I have P1 and P2. I do have X1 and X2. I can replace them to see what happens. Now, the question is, if I want to write down an equation for expected value of Wi, should I use 1 index or 2 index? If I want to write down this equation for expected value of Wi, I have to use 2 index. What are those 2 index? Summation j from 1 to 2 p sub j. Now, look at this x. What happened to this x here? The only change happened to this x is become lowercase, which is the realization. Now, I have to convert this w to lowercase letter. It will become w. And then I have to freeze I. And then I have to use another notation as j. Therefore, if this I is 0, then this equation will become j from 1 to 2, p sub j, w 0j. If this I is 1, then it will become p sub j, w 1j. If I is 2, then it will become 2j. Therefore, the expected value of Wi according to this relationship is 0. Which means that the expected value of our original random function is independent of n, is a constant. And that constant is 0. Which means that the first condition for stationarity is applicable. Now we have to go to the second step to see if the variance of our original random function is independent of n. Again, I'm going to replace y at n with summation I from 0 to n Wi. how could it be possible to compute variance of this summation? And tell the audience whether this variance is independent of n or not. What am I going to do, because we are going to use this relation numerous times, I'm going to talk about variance of random variable y in statistics, not geostatistics, to be a linear combination of n random variables. If I want to connect this to this, I would say here, out here, my a sub I is 1. Okay? And x of I is basically WR. If I can work with variance of y or variance of this summation here, find an equation for this case, or a relationship for this case, then I can use it here to find variance of this linear combination. For this linear combination, the coefficient is 1. Variance of y. Is basically variance of this linear combination. And then if I want to refer to basics to find the variance of this, I have to use this definition here. Not necessarily this definition, but this definition. Expected value of y at Si. This is point, not comma, which means that multiply. Y at Sj minus m at Si n at Sj. This is another way of writing covariance function. If you ask me how did you find this, I would say multiply this by this, simplify it to get that. What happens if I replace this j with I? If I replace j with I, I'm going to get expected value of y to the power of 2 minus m to the power of 2. Now, here, if you want to use that basic relationship, you would say it is equal to expected value of I from 1 to n, a sub I, x of I to the power of 2. This is y to the power of 2, which is equal to this summation, minus expected value of y to the power of 2. It is not okay to put 2 here, right? It is not okay to put 2 here. Charo? If you put 2 here, then expected value would not be raised to the power of 2. But this variance of y is equal to expected value of y to the power of 2 minus expected value of y to the power of 2. Here, it is better to first write this minus this. What I did, at first I write down this variance of y to be this, and then replace this y with what I have here. How could it be possible to raise this to the power of 2? I have to expand it first, get rid of the summation, and then raise it to the power of 2. When it comes to this, at first I have to protrude, activate expectation, and then raise it to the power of 2. Therefore, let me see what will happen. Expected value of, I have to expand this and then raise it to the power of 2. It will become a1 to the power of 2, x1 to the power of 2. Plus a2 to the power of 2, x2 to the power of 2. Plus an to the power of 2, xn to the power of 2. And then I have to time 2 times first times the second. Therefore, 2 a1, a2, x1, x2. Do you know what I'm doing right now? Just one of the identities in high school. Plus 2 times a1, a3, x1, x3, and so on. I expand this from y equal to 1 to n and then raise it to the power of 2 to get that. When it comes to this part, I have to first activate this expectation on xi, expand it, and then raise it to the power of 2. What would be the first sentence? a1 expected value of x1 to the power of 2. It will become a1 to the power of 2 and then expected value of x1 to the power of 2. That is the first sentence. Minus a2 to the power of 2, expected value of x2, then to the power of 2. And then you can generalize this and write a1 to the power of 2, expected value of xn to the power of 2. Then you have n terms here. Therefore, you have to consider 2 times a1, a2, expected value of x1 times expected value times A1, A3, expected value of x1, expected value of x3. Minus now, you can activate this expectation. I'm going to do two things simultaneously. I'm going to activate this expectation on this term here, and then collect terms to see what will happen. Let me write it here for Mr. Mir Ahmadi to be able to monitor what we are doing, because it is very different from what we did in our previous semester as opposed to this semester. ارزم به حضورتون variance of y we have to collect them. If I activate this E here, I'm going to get A1 to the power of 2 and then expected value of x1 to the power of 2, because I can bring A1 outside. And this A1 to the power of 2 with is there any other A1 to the power of 2? No. Therefore, yes, we have here A1 to the power of 2 as well. Therefore, I'm going to factor out A1 to the power of 2, and then it's going to be expected value of x1 to the power of 2 minus, how should I write this? Because I have already used this notation and I have used this notation, and then I should write this as expected value of x1 to the power of 2. What I did, I activate this, and then A1 to the power of 2 is common between this term and this term. I factor out A1, and then I'm going to get this. This is basically variance of x1. Plus A2 to the power of 2 expected value of x2 to the power of 2 minus expected value of x2 to the power of 2 Now, when it comes to this term here, look at this term. You have expectation being applicable to these two random variables, their multiplication of course, and then you have 2a1, a2 here. And then when you look at what you have here, you can factor out 2a1, a2. And then you have to put this here, expected value of x1, x2 minus expected value of x1, expected value of x2 and then please please pay attention that I have to put minus sign here. Why? Because plus or minus sign? No, plus. Because if you take expectation from this, it will become positive, which means that this times this will become positive. And then because this term is negative, this plus sign times this minus sign will become minus. And then you have plus 2 times A1, A2, A3. Again, expected value of x1, x3 minus expected value of x1 and expected value of x3 plus you can replace this with variance of x1, therefore variance of linear combination is equal to a1 to the power of 2 variance of x1 plus a2 to the power of 2 variance of x2 plus an to the power of 2 variance of xn. When it comes to this term here, you have 2 times a1, a2, covariance of x1 and x2. Covariance of x1, x2. Plus 2 times a1, a3 covariance of x1, x3. Now the question is, could it be possible to write down, by the way, I have to put plus a few points here to argue that it can go on and on and on. Now, could it be possible to contract, to write these terms as a double summation? First of all, let me see if I can write this part as a double summation. I can simply write this as single summation. I from 1 to n, ai variance of xi, that will take care of from here to here. This summation will take care of from here to here. Now, how could it be possible to represent from here to here by a double summation, assuming that y is not equal to j? You can simply write summation I from 1 to n, summation j from 1 to n, ai Aj covariance of xi, xj. But please pay attention that for this double summation, I cannot be equal to j, right? Because these terms are very distinct when it comes to the index. Therefore, you have to keep in mind that for this double summation, I cannot be equal to j. But you may ask, what happened to these two here? Can you answer this question? If I represent from here up to what I have by this double summation, what happened to these two? Can I reproduce two from this double summation? Yes. Why? Because I have to keep I equal to 2, I equal to 1, expand this summation. And then as soon as I will assume that I is equal to 2, then again j has to start from 1. Therefore it will create that 2 from here. Now, could it be possible to combine these two summations and write it as a single double summation? I can write this as I equal to 1 to n, I equal to 1 to n, a sub I, covariance of xi. Because variance of xi is equal to covariance of xi. This is how to replace this single summation with this double summation. And then plus this. If that is the case, then you can combine them. Because here I cannot be equal to j, but here I is equal to j. Therefore you can combine it into a single double summation, writing it as I equal to 1, j equal to 1, ai, aj, covariance of xi, xj. That is how to compute variance of linear combination. And if you took a course like Mr. Mir Ahmadi on advanced linear algebra, yes or no? Yes. Then you can replace this by a quadratic 4. Because we are talking about geostatistics, we can say, instead of having this x of I is a function of s, or this I is here. If this x is considered to be a function of spatial location, then you can write this as double summation I from 1 to n, j from 1 to n, a sub I, a sub j, and then covariance of x at si, x at xj. Because we are talking about geostatistics as opposed to statistics. And then you can replace this covariance by R. Summation I from 1 to n, summation j from 1 to n, a sub I, a sub j, r sub si, sj. And then, as I said, from linear, advanced linear algebra, you can write this as A as a vector, transpose R as a matrix, valence covariance matrix, times A. It's a quadratic form. Therefore, variance of linear combination can be written this. And that is what we did in our virtual lectures. A transpose valence covariance matrix A. Now, that is not our final problem. Our final problem is to see if the variance of y at n, which is this, can be shown to be independent of n or dependent on n. Now, Mrs. Rajab, could it be possible to tell me how should I write this variance of this linear combination based on what I have here? I can write this as I from 0 to n J from 0 to n A1 is 1, AI is 1, AJ is 1, and all we need to do is to write covariance of Y, WI, WJ. Just like what we have here. This is the linear combination, then the variance of this linear combination can be written this way. Now, how would it be possible to utilize this independent property? Because if I is not equal to J, covariance is 0. Okay? Therefore, we are left with a single summation because the covariance of Wi and Wj, if I is not equal to J, is 0. Therefore, it's going to be summation I from 0 to n, variance of Wi. Because covariance of Wi is 0 with Wj. Now, how could it be possible to compute variance of Wi? Again, refer to my previous lecture. Wi is a discrete random variable. I'm going to compute value just like what I did here, compute value, expected value of Wi. Here, I'm going to compute the variance of Wi. If Wi is a discrete random variable, then let me start with x and then extrapolate, generalize my equation to Wi. Variance of x, if x is a discrete random variable, can be written as I from 1 to n, piece of I times x of I to the minus mus of x to the power of 2. That is how to compute variance of x if x is a discrete random variable. Formula from statistics. Now, if I want to generalize this formula to what I have here in order to compute variance of Wi, I should write with double summation. I from 1 to n. By the way, this I should go from 0 to n. because I is also defined for 0. Or W is defined for I equal to 0. Then I have to put piece of I here, and then omega I have to put J, because I have I here, J ij minus mu Wi to the power. That is how to define my variance when I have Wi. The numerical value of W, mu sub Wi is 0. Why? Because we proved that the expected value of Wi is 0. Therefore, I'm going to compute this as 1 over 2 times plus 1 to the power of 2 plus 1 over 2 times minus 1 to the power of 2. It will become 1. And then when I'm here, I have to write this as summation I from 0 to n, 1. And what would be the numerical value of summation I from 0 to n? And then the argument of the summation is 1. It's going to be n plus 1. What happened? Variance of generic random function depends upon n. Therefore, it is not stationary. Expected value of Wi is independent of n, it's constant. But when it comes to variance of y sub n, variance of y sub n depends upon n. It should be constant if your random function wants to be stationary. But since variance of y sub n depends upon n, therefore your original random function is not stationary. Mr. Abudin, are you going to give this as a midterm exam? Is there a piece of cake? Now, it seems that we have to stop at this point and leave the remaining to our Saturday session. Okay? از حوصله و طمأنینه هم سپاسگزارم. همگی رو خدا بسپارم.